Now, the electric field of a uniformly charged disk is a case where we have the charge distributed over an area now, not over a length. Let's see how we can tackle this problem. This is the disk. Think of a CD, and you have a charge uniformly distributed over the area of this CD. Now, the radius of the CD is r, and its axis is along the x-axis. So this is x, this is your y-axis, the z-axis is out of the pin. So it is, this is the x-axis, and it is now coming out of the page. So this is how you have to imagine it, okay? It's coming out of the page, and the x-axis is at its center. So this is a 3D shape in this case. Now, and there is a charge Q uniformly distributed over the area of the disk. And so we know that we have now a surface charge density, a uniform charge density, which is Q over area, and this is over Q over pi r square, because the r is the radius of the disk, and this is your charge density, surface charge density, and it is has the units of Coulomb per meter square. Now I want to find the electric field generated by this disk at a point P along the positive x-axis. Now here, the idea is that we should make use of something that we already know, which is the electric field of a uniformly charged ring that we found in a previous example. So what we do here is we think that of the disk as being composed of rings, and these rings cover the whole area of the disk. So let me show one of these rings, for example. Consider a ring which has radius r, this is your ring, and it has a thickness dr. This is the thickness of the ring, it's dr. Now if you think of many of these rings with different radii that are all centered at the center of the disk, and they cover the whole area of the disk. Now, our idea is we know what is the electric field of each of these rings at the x-axis. We have found it, and we know that the expression for a ring, if you remember, we had this ring on the x-axis, and it used to have a radius a, and this distance was x, and the electric field here was E, and this E was k q divided by x square plus a square to the power 3 over 2, and I had an x here, kx, and it was along the along I hat. So this was the expression for the electric field of a ring, and it was along the x-axis. Therefore, each of these rings will contribute an electric field given with this by this expression, and it will be along the x-axis. Of course, the variables here will correspond to the variables corresponding to each ring by itself. And then when we add them up all together, then we will get an electric field which will be also along the x-axis, along the positive x-axis. So without doing any calculations, by trying to conceptualize the problem, we managed to get to know now what will be our approach. The first thing, it is that, well, we divide split this into small rings, find the electric field of each ring, and then build them using the expression that we already know, and then add these all together to cover the whole charge distribution on the ring. And that we know now that also for the disk, the electric field will be along the x-axis, because each ring will contribute a field exclusively along the positive x-axis. Okay, so this is how will things unfold. Now we are ready to go to the analysis stage, that is to quantify things. So the first thing, therefore, is to identify, okay, we have identified already that this is our dq. So our dq now is the charge of each of these rings. Well, you can think of this as it is a ring, but it is not of zero thickness. It's like of a strap, okay? You bring it into the form of a ring, so it has a given thickness here, and this is your dq, and the electric field of each of these dq's, dE of this dq is k dq. This distance is still x over. Now, the radius in this case is not a, but r. We have changed into r. So we replace just a in that expression by r. So it's r square plus x square to the power 3 over 2. So this is the electric field, and it is along the x direction. I don't put dEx here because we know this. So this is the electric field generated by each of these straps. So this is the first step in the analysis. Now step number 2, okay, what is my dq? I should express dq in terms of the charge density and so on. Well, dq, as we have discussed in the theory part, dq is actually sigma multiplied by dA. dA is the area over which this charge density is distributed. Now, what is this, which is this area? Because the ring now has a finite thickness, then the charge is distributed over an area actually, so it has an area. Now, what is the area of this ring? It is actually, this dA is equal to 2 pi r dr. This is the circumference multiplied by its thickness, okay? So dr, because it's small, when dr is small, this is a good expression, and so therefore my dE in this case will be k sigma x 2 pi r dr divided by r square plus x square to the power 3 over 2. And this is the expression for dE, okay? After substituting for dq in terms of the charge density multiplied by the area element. So this is the expression. Now, the next step is to add up all these dEs, in other words, to integrate. So my E is integral over dEs, okay? And this will be integral over k sigma. Let me write it in a more compact form. So we can write it as 2 pi k x sigma r dr divided by x square plus r square to the power 3 over 2. Okay? So this is when you integrate. Now at this stage, I start probably to identify what will be my integration variable. As I always say, this dr that appears here gives you a hint. Okay? So it seems that r is our integration variable. Is it really our integration variable? How to check? Well, actually, the integration variable is the quantity that when it varies, okay, you are adding the contribution of all the dq's. And this is exactly what's happening, because you know we thought of this system as being composed of rings of different radii that covers the whole area of the disk. So indeed, as r varies, then you are taking the contribution of all the disks of different radii. So r is an integration variable. Now, what are the limits of this integration variable? Well, you want this variable r to vary so that it catches all the dq's that form for you the disk. So it should vary from 0 up to r, capital R, because this is where the charge distribution is, where charge is distributed. Okay, so we make this go from 0 to r. Now I know that 2 pi k x sigma, all of these are constant. I take them outside the integral, and I got this as 2 pi k x sigma, the integral of 0 to r. Let me keep this here. You can keep this as 2r dr divided by x square plus r square to the power 3 over 2. Okay, so this is your integration, and what remains is to carry out this integral from 0 to r. Now this integral can be carried by substitution by noting that 2r dr is actually dr square. Okay, so you can write this as pi k sigma integral from 0 to r d of r square divided by x square plus r square to the power 3 over 2. This is a shorthand for substitution. Actually, what you do is you make r square u, and this will be du, and so you will have here x square plus u and the integral over u. Whatever is this, you calculate the integral, and the result, it is a simple integral now, and the result is that this is x squared plus u, if you like, to the power minus 3 over 2. It is just this denominator to the power minus 1/2 divided by 1/2, so it becomes e becomes pi k sigma, and it is x square plus r square to the power minus 1/2 divided by minus 1/2, and the limits of integral are from 0 to r. Now, if you work out this integral and the limits and collect things together, take this outside and take do I have an x? I think I have an x somewhere here. Yes, we have an x here. So this x should be here. So I should have the x here. And if you do these, then you will get the following: minus 2 pi k sigma x multiplied by. Now you take the minus sign outside, so the upper limit in this case will give you 1 over x square plus r square to the power 1/2 minus the second you substitute for r0, so it will be 1 over x squared to the power, which will be 1 over x minus 1 over x. Is that correct? So this is 0, and this is x squared to the power minus 1, so it's x to the power minus 1. Yes, exactly. And so this reduces to, if you let x n and also the minus sign in, this will be 2 pi k sigma 1 minus x over square root of x square plus r square. Okay, so this is your E. And if you want to make it a vector, you say, okay, this is my vector, and it is along the positive x direction. So this finalizes your analysis, and you have got the answer. Now, we need to verify or to check this answer. Well, there are two checks. First of all, let me see that it gives me the electric field in the direction that I expect. I mean, this should be, this quantity should be positive because it is along the positive x direction. Indeed, this is a fraction, this is 1, so the whole bracket is positive. Everything here is positive, so this is again indeed pointing in the positive x direction for a positive sigma, of course. If sigma were negative, then in this case, this would be pointing in the negative x direction. So as far as direction is concerned, it's okay. The second thing is the units or the dimensions. Does it have the correct dimension? Now the bracket is dimensionless. There are no units here because length over length, 1, and this is 1. So it should be, I should look at this. Does this have the correct limit, which is K multiplied by Coulomb divided by meter square? Well, K here multiplied by sigma. What are the units of sigma? Coulomb divided by meter square. So it's K multiplied by Coulomb divided by length square. So it's okay. So as far as the limits, as the units are concerned, also this is okay. Now, there is an important expression that I get in some limit, in the limit of large disk, and this we will be considering later in, when we discuss Gauss law in particular. We will rederive that expression, which is the electric field of a large uniformly charged plane. Okay, so when the disk becomes very large in comparison to this distance, then as if you have an infinite plane of charge and you are trying to find the electric field above that infinite plane of charge. And let's look at this limit. So the limit of an infinite plane of charge. How do you make this infinite? You make R very large. So you make R goes to infinity. In this case, E goes, when R goes to infinity, as you can see, this quantity becomes 0 because this is very, very large, and this becomes 0. So this goes to 2 pi K sigma I hat. Okay? And if you substitute K as 1 over 4 pi epsilon naught, then this becomes 2 pi over 4 pi epsilon naught multiplied by 2 pi, multiplied by sigma I hat, and these cancel, you get, so it becomes sigma over 2 epsilon naught along I hat. And as far as a magnitude, E modulus in this case will be sigma over 2 epsilon naught. Now this is an expression, which is an important expression. This is the electric field of a uniformly charged infinite plane. And we will rederive this later. This is one of the important limits of the disk.